Ja, herzlich willkommen zurück zur Data Disrupted. Wir machen weiter im Nachmittagsprogramm. Jetzt zu Gast Peter Buschmann von Booking.com. Der Vortrag selbst ist eine Aufzeichnung, aber der Peter ist live dabei. Der kann eure Fragen beantworten. Einmal im Chat. Den Chat ist die ganze Zeit offen. Und wir werden zum Schluss auch die Mikrofone aufmachen. Dann könnt ihr auch diskutieren, noch Fragen stellen mit dem Peter, der dann auch wieder mit der Kamera zu uns geschaltet wird. Ja, worum geht's? Nimm SSDs, haben sie gesagt. Mach Jumbo-Frames, haben sie gesagt. Mach Fiber Channel over Ethernet. Wirklich? Peter Buschmann von Booking hat alles ausprobiert. Peter, was ist wirklich dran an diesen ganzen Thesen, ne?
Hello, and welcome to Lies, Damned Lies, and Best Practices, Storage in the Age of Abundance. My name is Peter Bushman, and I'm proud to be representing Booking.com here at Data Disrupted 2020. First, a word about Booking.com. We are the majority part of Booking Holdings, formerly the Priceline Group. We are one of the largest e-commerce websites in the world, and we are the largest online accommodation website in the world. We service over 1.5 million properties in over 220 countries and territories, with 1.55 million room nights booked every 24 hours. We have over 15,000 employees in 198 offices in 70 countries, with thousands of LUNs, NFS shares, and S3 buckets, managed by a storage team of only 4 people. Things have changed a bit with the impact of COVID-19, but I don't have any newer numbers to update this slide with yet. I'll keep you posted. There are 3 kinds of lies: lies, damned lies, and statistics. Or so goes a popular quote from the 19th century, often misattributed to Benjamin Disraeli. It is a reference to the persuasive powers of numbers, particularly their ability to lie and lead people to believe conclusions they do not actually support. My version refers to best practices in the area of storage. You've probably encountered them in the form of reference architectures, white papers, or even just conventional wisdom about how storage is done. The problem with these best practices is that they are rarely reevaluated to see if the march of technology has reduced their relevance or even invalidated them altogether. Believable lies always start with a kernel of truth. We believe them because they sound plausible. Best practices that have become lies are the same. They once were true, except that the conditions that caused them to be true ceased to exist. Best practices are always situational, and we should constantly be checking to see if those situations have changed. During my 5-year career at Booking.com, I have successfully violated many of the best practices that were drilled into me during the preceding 20 years in the storage industry. The old me would have some not so nice things to say about what the current me is doing. I might as well have titled this talk Storage Worst Practices. According to industry best practices, many of our storage architectures shouldn't even be working, let alone keeping a billion-dollar website running, except that they do. A colleague of mine, Chris Kerntop, coined the term the data center in the age of abundance. This is what he has to say. We are currently experiencing a fundamental transition in the data center. In the past, 3 fundamentally scarce resources limited the systems we could build: IOPs, bandwidth, and latency. All 3 of them are gone to a large extent, and the systems we are discussing now are fundamentally different from what we had in the past, with the past being a thing 5 to 10 years ago. At Booking.com, we've had the luxury of implementing quite new infrastructure. We have been able to operate without these traditional constraints for some time. And yet, when I talk to storage and server companies, I see many of the same best practices being recommended blindly, as if the old constraints were still in place. This is a talk about storage best practices. specifically ones that have become worse practices in the age of data center abundance. I am not saying that any of these are fundamentally bad, just that if you are designing storage architectures in 2020, you might want to consider if some of the principles you followed in 2010 or 2000 still apply. In many cases they don't, but people still follow them anyway. Today I'm going to share 6 of them with you. Number 1 on my hit list is jumbo frames. Despite the fact that this is 2020 and Ethernet has hit 100 gigabits per second and faster speeds in recent years, I regularly encounter vendors and products that blindly recommend using them as a best practice. It drives me crazy. This is so ingrained into the conventional wisdom of network storage that it is even the default setting on most products I encounter. Jumbo frames are nothing more than Ethernet frames with a payload larger than the standard 1500 bytes. They've been a thing ever since 1 gigabit Ethernet came out, but have always been a non-default setting that required support from your NIC and switch vendors. Sending more data with fewer packets is more efficient, so why wouldn't you want to do it, right? It sounds like a really great idea, but it can be a nightmare to implement in practice. You see, 1500 bytes is the default everywhere in your network. It is the default on network cards, switches, routers, firewalls, hypervisors, and operating systems. To get the efficiency benefits of jumbo frames, you literally need to change the default setting everywhere. Changing this setting universally is not only a daunting task, the effects of missing it somewhere can be non-obvious. I try never to change default settings if I can, but this is one that I keep being told is required. When I question why, I am bluntly told it is for performance. Here is the amount of extra throughput jumbo frames extract out of every generation of Ethernet from 1 gigabit to 100 gigabit. The efficiency is a constant 5%, so by the time you get to 100 gigabit, you're getting a whopping 5 gigabits per second more throughput. That sounds like a lot, right? Hey, it's 5 times the 1 gigabit speed we had when we started. That sounds pretty good, doesn't it? But if we compare this to the generational increases in bandwidth achieved, this is far less impressive. Across the range of speeds available today, there is an average increase of 247% in bandwidth versus the next lower speed. Between 1 gigabit and 100 gigabit, bandwidth went up by 9,900%. If you have implemented any generation of Ethernet in your data center since 10 gigabit came out back in 2007, the generational change has brought you an order of magnitude more performance than jumbo frames did on the previous change. If you have made more than one generational change, then the effect of jumbo frames is a rounding error. In the age of abundance, we are drowning in bandwidth. Jumbo frames are no longer worth the complexity they add to your network. Number 2 on my hit list is fiber channel. If you've been anywhere around storage in the past 20 years, you may have heard about storage area networks and its flagship technology, fiber channel. As the name suggests, SANs are a separate network for storage, only storage. As late as 2017, we were still operating substantial fiber channel SANs. We began using them when our data center network was just 1 gigabit, and without them, we could not have provided a reliable storage infrastructure to our internal customers. However, it came at a great cost. Instead of a single data center network, we now had 3, 2 of which, fiber channel fabrics A and B, were a walled garden, accessible only to a tiny subset of our 50,000 plus compute fleet. It was also as single purpose as it gets, and required a special skill set to operate. Only block storage worked on it, and none of the cool new technologies like parallel file systems or object storage were compatible with it. Over time, our data center network was upgraded. We got 10 gigabit compute nodes and a 100 gigabit network backbone. Suddenly, our entire data center was faster than our SAN had ever been. So much so that we were actually able to deploy slightly slower storage protocols such as iSCSI and still give our users better performance. Today, fiber channel is long gone. Instead of a walled garden with a few hundred servers connected to it, we can provision storage to any server in our compute fleet with no special infrastructure. We only have a single network to maintain, and it serves all sorts of traffic, not just storage. The storage analyst Howard Marks once made a comment that fiber channel is like smoking when you're over 40. I agree with him. If you're not doing it, you really shouldn't start now. And if you are doing it, your doctor should be advising you to stop. There are plenty of statistics I could cite to support my case that fiber channel SANs are no longer a best practice. On performance and density, Ethernet is winning across the board. However, cost is where the difference becomes clear. I Googled these prices recently, but you should find roughly the same differential from your favorite networking and storage supplier. 100 gigabit Ethernet is 30% cheaper than 32 gigabit fiber channel. What's that, you say? 30% doesn't sound like that much of a premium for a superior technology? Maybe not, but look at the speed. You can match the speed of 3 fiber channel ports with a single Ethernet port. 3 times 32 is 96 gigabits per second. Incidentally, that's about the same throughput you can get on 100 gigabit Ethernet without needing jumbo frames. Pretty cool, huh? So while the HBAs and ports are only a modest 30% more expensive with fiber channel, you are getting 2/3 less bandwidth than with 100 gigabit Ethernet. On a bandwidth basis, this makes Ethernet 75% cheaper to acquire. That huge disparity in bandwidth cost can be put to very good use, as I will explain next. Lossless Ethernet is another one of my bugbears. It is right up there with jumbo frames for the number of times I encounter it as a best practice, if not an outright requirement espoused by certain vendors to make their products work optimally. Like jumbo frames, we've been told we need this for so long that we forgot why it was necessary in the first place. The answer, as with many things in the age of abundance, is scarcity. In this case, scarcity of bandwidth and the fear of losing packets. It all began with 10 gigabit Ethernet, which was just fast enough that you could share it with multiple protocols. Instead of the walled garden of fiber channel, storage over Ethernet was like the Wild West. All applications competed with each other, and when the network got saturated, Ethernet's response was simply to drop packets. Storage is very sensitive to this and also sits at the bottom of the application stack. Bad things could and did happen in those days when you ran out of bandwidth. Quality of service was invented to solve this problem and allow applications to share a congested Ethernet without suffering too greatly. Fiber channel didn't have these problems because it already had congestion control mechanisms built in. You could saturate fiber channel, but you wouldn't lose packets. And so lossless Ethernet was born. It is so pervasive now that it shows up in the requirements list for most new Ethernet-based block storage products, particularly anything having to do with NVMe over fabrics. I've even had vendors swear that their products would not work without it, and be shocked that we were not exactly willing to run around changing the settings of every switch on our network just because they said so. It turned out our network was already lossless, despite not using any of the settings that are supposedly necessary to achieve this. When applications require lossless Ethernet, they are not specifying how that losslessness is to be achieved. Just because a network is lossy doesn't mean it drops packets randomly all day long. Dropping packets is a congestion response, nothing more. Our answer to lossless Ethernet was simply to have more bandwidth than we needed and to undersubscribe our switches so that congestion did not occur. A congestion-free network does not drop packets. The nice thing about bandwidth as a mechanism for achieving losslessness is that it is universally interoperable. The collective standards that make up lossless Ethernet are not. Next up, we have good old RAID controllers. At Booking, we buy thousands of enterprise servers every year, and RAID controllers are a standard option, so much so that RAID 1 mirrors are the default setting on most of our compute fleet. A few years ago, we stopped buying hard disks in our compute nodes, but we kept buying RAID controllers in them because nobody questioned it. RAID was a best practice with hard disks, so surely it must also be the case with SSDs. Only the media had changed, not the drive bay or the server around it. I decided to question this. RAID controllers add several €100 worth of cost to each server. That adds up over thousands of nodes. I began to wonder if we still needed them. Why did we buy RAID controllers in the first place? Surprisingly, protection from drive failure was only a secondary concern. Performance was the main one. Each RAID controller came with a large amount of cache that served as an essential buffer for writes, protecting the application above from the high latency of the disk. Did we still need this function? At first, yes. Some early SSDs were horribly unreliable, and performance could be quite unpredictable. The reliability issue got resolved, though, and now we see a failure rate typically 10 times lower than HDDs. If drives were no longer failing, what were we protecting against? Next, there was the performance issue. At Booking, we require steady, predictable write latency. Had that gotten any better? To find out, we compared two servers that had identical CPUs, memory, and SSDs. The only difference was that one had a RAID controller and the other just had a plain SAS controller. Which one was faster? The one without the RAID controller won hands down. The generational improvements in SSDs over the past several years have been such that just one average enterprise SSD these days can deliver more performance than the RAID controllers we were plugging them into. What is more, the drives were so responsive that it was actually slowing them down by putting the RAID controller in the middle. RAID controllers in our servers were not only adding cost, they were adding latency. We haven't bought RAID controllers in our servers since. They still have their place the way we originally used them with disk drives, but they have no place in an all-flash server. Moving on from networks and controllers, I'd like to close by picking on two types of storage media. My first victim is the venerable SAS disk drive. SAS is short for Serial Attached SCSI, and it has been a mainstay in the data center for many years. Just 5 years ago at Booking, we had racks and racks filled with thousands of SAS disks aggregated behind storage arrays. Today they are all gone, every last one of them. But we are buying more disk drives than ever, nearly an exabyte worth. None of these are SAS. Why? Our buying patterns have changed dramatically. SSDs have taken over all performance workloads. This has eliminated 15,000 RPM and 10,000 RPM SAS disks from our environment. HDDs have been relegated exclusively to capacity workloads, driving a growing demand for high-capacity nearline disks. As a media interface, SAS now finds itself in the position of being too slow for SSDs and too fast for HDDs. Unlike Goldilocks and the Three Bears, however, being in the middle is not just right. All of the high-capacity disks we are buying are available with either SAS or SATA interfaces. The difference in cost is marginally in favor of SATA, but that is not why we don't buy SAS. We don't buy SAS because we don't need it. Although 12 gigabit SAS has twice the throughput of 6 gigabit SATA, no nearline disk can transfer data that fast. The mechanics of the drive are the same, just putting a faster interface on it does not make it faster. We've benchmarked the drives and simply cannot tell the difference from a performance standpoint. Not only is SAS too fast for the drives we are buying, its ability to chain hundreds of drives together in shelves no longer serves a purpose. External disk shelves have disappeared from our server estate because the bottleneck has moved away from the storage backend to the server and the network. It takes relatively few high-capacity disks to fill up a server. Our smallest machines have 16 drives, and our largest have 60. You don't need SAS for those footprints. SATA is fast enough, SATA is slightly cheaper, and SATA uses slightly less power. SAS is no longer a best practice, not because it isn't good enough, but because it cannot compete with good enough. In an age of high-capacity nearline disk drives, I consider SAS to be the storage media equivalent of the Volkswagen Karmann Ghia. It has a nicer chassis than the Beetle, but the engine is the same, so it doesn't go any faster. My final target is another piece of storage media, write-intensive SSDs. Nobody should be buying these, and if you are, you absolutely should not be paying a premium for them. Here is why. At each capacity point, there is no physical difference between a write-intensive and a read-intensive drive from any of the major manufacturers. The flash is the same quality, and the same amount of it is used to manufacture the drive, regardless of how it is marketed. The only difference is the amount of over-provisioning of NAND flash in the drive. Over-provisioning is the amount of flash reserved for garbage collection and wear leveling. The more you have, the more writes you can sustain before the flash wears out. Drive endurance is measured in drive writes per day, or the number of times per day a drive can be completely overwritten within its warranty period, which is usually 5 years. In the early days of SSDs, manufacturers were absolutely paranoid about drive wear, and write-intensive drives with DWPD values of 5 or 10 were common. These days, a value of 3 is generally accepted as good enough for high write applications, while a value of 1 or less is marketed strictly as read-intensive. I really hate these terms because they imply that these drives are better at one particular function than the other. They are not. Write-intensive drives are just as good at writing data as read-intensive ones, and read-intensive drives are just as good at reading data as write-intensive ones. Think about that for a second. If the drives are the same, why would you choose one over the other? The choice is presented as one of endurance over capacity, but the reality is that write-intensive drives make that choice for you, while read-intensive ones let you choose, and even change that choice depending on the situation. If you write the same amount of data the same number of times to a read-intensive drive as to a write-intensive one, it will last just as long. The difference is that you need to be disciplined enough to not use all of the space the drive makes available to you. By partitioning a drive and leaving some portion of the space unused, you can actually turn a read-intensive drive into a write-intensive one with any DWPD value you want. Some manufacturers will even give you a tool to do this. Let's look at two versions of a high-capacity SSD. Several manufacturers have the same specs. The write-intensive drive advertises 12.8 terabytes of capacity, and the read-intensive drive advertises 15.36 terabytes of capacity. Both drives have the same amount of NAND flash, 16.38 terabytes. The read-intensive drive is over-provisioned by 7%, while the write-intensive drive is over-provisioned by 28%. In all other respects, these drives are identical. If I only use the first 12.8 terabytes of capacity, the read-intensive drive will behave the same as the write-intensive one. The difference is choice. With the read-intensive drive, I can choose if I want capacity or endurance. I can use all 15.3 terabytes, or if I want to be extreme, I can partition down to 50% or even 80% to create a super endurant drive. I don't need the drive that is marketed as write-intensive to do this. It is just working as designed. Effectively, I can dial endurance and capacity to whatever level I want. Don't buy write-intensive SSDs. Buy the read-intensive version of the same class of drive and then choose how you want to use it. I've taken you through 6 worst practices in the age of abundance in the data center. Jumbo frames, fiber channel SANs, lossless Ethernet, RAID controllers, SAS disk drives, and write-intensive SSDs. All of these were originally best practices, and depending on where you are in the technology cycle, might even still be relevant. However, if you find yourself choosing any of these technologies as part of a new storage project, you might want to think about the alternatives. An abundance of bandwidth, IOPs, and low latency presents us with some amazing choices from which entirely new best practices will be defined. In conclusion, I'd like you to ask yourselves this question. What lies have you been told lately? Who gave you storage advice that you didn't question? Is something that seemed like a good idea 4 years ago still relevant in the age of data center abundance? Question, 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 and find the facts. The truth might surprise you. Thank you very much.
Dankeschön. Vielen, vielen Dank, lieber Peter.